Okay, 11.7 is just kind of a summary, a recap of the different rules we've learned before we head into 11.8910, which is getting us into Taylor and Maclaurin series. Okay, so this is our last little hurrah before we sort of dive into the next idea. So things we need to keep in mind, so everything from like 11.3 up to 11.6, we have to know that p-series are always available for both for comparison purposes and for just for themselves. We know that p-series converge when p is greater than 1. So we have, what's a p-series? 1 over x to the p. Okay, so that's what we're talking about. That's a p-series. Okay, so we know that 1 over n diverges. That's the harmonic series. But of course, if we're alternating, then we get conditional convergence on the alternating harmonic series. We know geometric series converge, and it's very, very useful for comparison, and a lot of our limit test, ratio test, whatever, are based around implicitly comparing to geometric series as a whole. We have alternating convergence. I kind of think of it as a last resort mathematically, but it's not a last resort in your chain of command, because as soon as you detect an alternating situation, then you kind of, your curiosity gets piqued and you think that might be the direction the question is going. If the terms don't go to 0, then obviously this series diverges. And sometimes when you're deep in the midst of everything else, you miss this obvious fact. So it's just another thing to put on your mental list. Factorials are often a good bet to use with the ratio test, but beware, don't try to use the ratio test with p-series or things that are very close to p-series, because then you'll just get equals 1 in the limit, which tells you absolutely nothing. So don't be tempted to think that the 1 means anything. If you get a 1, that means you used the wrong test. And if your terms all have a power of n in them, then again, you're just thinking in terms of geometric series, really. And you use the root test, and that'll get you out of that mess. If the integral is easy, or a bounded version is easy, so for example, like if, you know, this integral plus x plus 7, that's obnoxious, but you could bound that up or bound that down and integrate that pretty easily, right? So even though that integral, you can't really tell where that's going, but you can definitely use the integral test on something like that to demonstrate convergence. Okay, so this little thing was name the strategy, but the answers are all here, but this is what we went over in class. So if in this case we see the terms don't go to 0, we have an n over 2n happening, so it's 1 over 2. Excuse me. So since the terms are not going to 0, then the whole thing's going to diverge. The next one, you kind of compare against p-series. You can look and say, well, n cubed and then square root, it's like n to the 3/2, and then the bottom is like n cubed. Forget the 1 over 3. Who cares about that? It doesn't affect convergence. And then it just, you know, you find out, oh, okay, so this is like 1 over n to the 1.5. That's actually going to converge. So this big mess, you just work out the exponents and you compare against a p-series. We talked about this one. We used an integral test on that because we got u substitution going there. That works. Or you could do a ratio test. That thing converges. Okay, the next one we have alternating. So we want to make sure there's no absolute convergence before we go ahead and say there's conditional convergence. So we look at the n cubed and the n to the 4th as 1 over n. So that thing is definitely, it looks like a harmonic series, so it's not going to converge absolutely. But if you throw in the -1, it's alternating, these terms are decreasing to 0, we're good to go. Okay. Next one, 2 to the n over n factorial. Well, if you remember my little lineup, n factorial is going to win over 2 to the n. So that's good to go. But let's figure out what we're going to use to prove that. So you think, okay, we can try the ratio test. Yeah, it goes to 0. What it's saying is that it's even faster than a geometric convergence because you have kind of the common ratio between terms is 0. So let's say you have 100 is the first term, and the next term is like a tenth, and then the next term is like, no, if you start from 100 and the next term is 10, sorry, and then the next term isn't going to be 1, it's going to be smaller than 1. You're saying that like if the common ratio were 10 at the first step, then or 1/10, and then the common ratio is smaller than a tenth at the next step. So this thing is, you know, geometric convergence is pretty fast. This is faster than geometric convergence. What it means is after a few terms, you're not even going to notice that 2 to the n. It's just going to be completely washed out. It's just not even going to exist. And that's what this ratio thing is telling you too. That 2 is just going to get washed out over n plus 1. And finally, this plus 2, don't worry about it. You know, this 1 over 3 to the n is really what's going on there. And the plus 2 is just to throw you off. So you just do a compare with 1 over 3 to the n with a ratio test, and then it'll just come out nice and easy. Okay?